Okay. Good afternoon, all of you.
Good afternoon.
Yeah,
Yeah,
shall we
shall we
start?
start? Yes, we can start now.
Okay.
Okay. So,
So, very good afternoon. So, let us continue with the discussion and the last class of this tropical equatorial ocean dynamics as part of the skill development program. I hope you all have understood what we discussed in the last three classes, and you had spent some. I hope you had spent some time to go through the material, try to understand more tropical ocean dynamics, and have gone through the toy model we have supplied, and you have made a good use of it. I hope that. So let us continue with the remaining part of the discussion today. So yesterday, let me give a recap what we have discussed yesterday in the tropical wave discussion. Yesterday's discussion basically focused on how what are the latitudinal extent these waves can penetrate to the away from the equator. So we introduced a concept called critical latitude. So critical latitude is a latitude up to which the beta plane, equatorial beta plane dynamics is kind of valid, or the associated Hermit polynomial mode, meridional mode number go and end up at what latitude, okay? What latitude is going to terminate. So that is what we discussed yesterday, and I will share my screen before beginning further uh, lecture. So we have seen that the critical latitude we found with the simplest understanding by the after supplying the most generalized wave solution of the form v equal to v naught exponential I kx minus omega t, you get this equation in v, which says that as v tends to 0, as y tends to infinity, giving us you a privilege of taking this the term on the second term here equating to 0, which gives you kind of condition beta square y square c square, or yc square. Yc means the critical latitude, equal to whatever remain in the right hand side. So it simplifies to beta square yc square equal to 2n plus 1 beta by c. If you proceed with this for a first baroclinic speed of 3 meter per second and beta of 10 to the power minus 12, and for a meridional mode n equal to 1, you're gonna get around y critical latitude to be around 28 degree north or south. That is the tropics of our discussion. Okay, that's the tropical area. Therefore, y is the critical latitude or turning point for tropical waves. Similarly, one can prove the maximum frequency of long waves in the long wave limit or in the short wave limit also. For example, in the long wave limit, the maximum frequency possible is something related to c by 2 yc, or frequency is inversely proportional to critical latitude, or the other way, critical latitude is inversely proportional to frequency. If very low frequency wave can go larger and larger latitudinal extent away from the equator, and high frequency tropical waves or equatorial waves are constricted more close to the equator. Their critical latitude or turning point is much closer to the equator. So we have discussed the schematic. Say, for example, an annual Rossby wave can propagate all the way. Propagate mean can be present all the way at a latitude around 30 to 40 south, but a semi-annual Rossby wave can, however, has to return back much early latitude, and intraseasonal waves of high frequency cannot penetrate deeper into high latitude. So it has to be very strictly bounded to the equatorial region. So and after that, in yesterday we discussed several Haumüller diagram. If you remember, we have discussed what are the Haumüller diagram for a Kelvin wave, what is the Haumüller diagram for a Rossby wave, and etc. We have discussed, and we calculated the velocity of each of these parameter derived theoretically, as well as the uh, what as well as the Haumüller diagram calculated space speed. We compared; they were agreeing closely each other. So the theory what we studied is what really we see in the real ocean. So today I will focus on two more remaining aspects. I mean, one aspect is that why we need to study the tropical waves, and what is its real application, or where is it where it can be applied readily, so that you understand some existing natural phenomenon in terms of these tropical waves. One such example is El Nino and southern oscillation. So you might have heard of the word El Nino and southern oscillation. Most of you may be already aware what is it actually about. Now, the point of today's discussion is that whether the waves we study today is going to can be used to explain the mechanism underlying El Nino. That is the question we are going to ask. Probably yes, we can apply the principle. So it is a good time to associate what we study in the theory in a real size problem. Okay, so that you will give some insight. You'll get some insight on the fundamental mechanism. The other topic we want to discuss is the little more about say yesterday we discussed the the mixed Rossby gravity waves is a part of the tropical wave curve, right? For example, if you look at your wave number frequency diagram, so this is your wave number frequency diagram. So yesterday we all studied about a Kelvin Rossby wave, something happening in the westward direction of minus k, and plus k is the Kelvin. Another one, some waves, however, we studied is straddling between Rossby wave and and gravity wave. So this is the gravity wave regime. Okay, so these waves are straddling between Rossby wave and gravity wave. We call it as mixed Rossby gravity wave. So these are of special interest of waves because in the low frequency omega side, they behave as a Rossby wave. They propagate westward and their group velocity is eastward. So yesterday we discussed if you take the curvature of this curve, you will get the group velocity which is going to the eastward direction if you take the derivative of this. So then and that they are mostly of a kind of a high wave number, and they may be short in size. As the wave number increases, the waves lambda decreases, right? And then and the low frequency high frequency side, when the omega increases, you will find there some nothing but inertial gravity waves or gravity waves. So let us try to see how to simulate this. Yesterday we briefly touched upon how to simulate such waves or why these waves are so important. So one interesting part is that you can simulate such waves if you have a tropical ocean of this size. For example, this is your tropical ocean, and this is your equator, for example. Okay, now if you assume this is, say, for example, 40 degree, oh sorry, 40 degree east, 40 degree east to 140 degree east, say 100 degree depth width. Okay, and this is our tropics, 20 degree south to 20 degree north. Okay, so in this case, suppose if you are forcing the ocean, the previous example we considered as the forcing the ocean in the zonal direction. Our forcing we kept at some place here as the wind forcing. Then we study Kelvin, Rossby, and all very beautifully we have studied. But today, suppose if you give a forcing in this meridional direction, what would happen? What would happen? Definitely the mass of this part of the ocean has to be pushed forward, and because of that it is going to build up as a positive mass zone or high sea surface height zone in the north, and what is mass pushed in the north is will be devoid from the south, so you will have a negative sea surface height on the southern part of it. So this is positive sea surface, positive, and this is negative. Okay, so a counterpart you can draw on the right hand side. There will be another negative forming here because they are of wave, they're asymmetric structure wave, right? And there will be a positive component in the south. So this is called a mix. This is a typical shape of a mixed Rossby gravity wave with the westward phase propagation. Now if you take the velocity of associated with this tropical wave, so if this is a high pressure, what will be the geostrophic principle? You will have a what kind of circulation you will have if it is high pressure. So the water will be circulating in the clockwise direction, right? This will be the circulation of water. If it is a low pressure here in the south, what will be the direction of water circulation? So the pressure gradient is inward, so to the left it has to circulate. So again there will be a circulation in this direction in the southern part of the wave. So basically there will be a cross equatorial flow set up by this type of wave. This is the typical mixed Rossby gravity wave, and this is very common. Why this is common we have to discuss. Which it has a cross equatorial flow, the flow crossing the equator in this direction you will see due to the presence of this wave. The other component you can draw here also. For example, if you follow the geostrophy, you can get the cross equatorial flow in this manner. Okay, so this kind of wave has a kind of a westward phase propagation and eastward group propagation. So let us try to simulate it. And why is it so important? Because if you come to the Indian Ocean, you know all the Indian Ocean by now, right? Let's draw a schematic of the Indian Ocean. So Indian Ocean is rather simple. You have Indian Peninsula and Sri Lanka. Then you will have the Bay of Bengal in the right side, right? So this is your Bay of Bengal, and this is the equatorial region, and this will be your Arabian and what the Arabian coast, right? So you will have your Red Sea here and one more ocean here, and then going to the African continent and some Madagascar. So if you take the equatorial region of the Indian Ocean, we all know that Indian Ocean is experienced by strong monsoonal winds. So this is our southwesterly monsoon, right? And this is the opposite will be our northeasterly monsoon. So we have these two types of monsoon circulation exist in this. And is this monsoon circulation uniform seasonally? No, they have a high intra-seasonal oscillation, right? If you examine, they have intra-seasonal oscillation of 20 to 60 or 20 to so 90 days of scale. It's a broad scale, I am saying. Okay, 20 to 90 day of scale intra-season oscillation. That means you will have a strengthening of the wind during some part of the days and weakening of the wind. Again, strengthening of the wind, again weakening of the wind. That will act as a y directional forcing in this shape. So the meridional component of the wind will have an oscillatory nature, something like this, and that is very good wind for generating mixed Rossby gravity waves, because the situation we already explained. If the wind is blowing to the north and it pushes the mass to the north, so it has to evolve as a MRG wave. And wind is going to the south, the opposite condition can happen. Once the wave emanates, it cannot stay there, it has to propagate. So that's why we are particular about this type of forcing, the north-south forcing, and that is very much observed in the Indian Ocean. If you know the Indian Ocean well, you know that Indian Ocean has intra-seasonal oscillation during monsoon, summer monsoon season. So another one way of interpreting the intra-seasonal oscillation is that strength of this jet, the southwest monsoon wind speed. So they will increase and decrease according to say 20 to 60 day times or 20 to 80 day, 90 day time scale. So accordingly, the meridional component will have an anomaly of positive anomaly and negative anomaly, right? The meridional component of the wind. This is wind I am plotting about, okay? The V wind, okay? So V wind will oscillate in this way, which generate trains of mixed Rossby gravity wave in this region. And this is actually, by observation, people have observed such mixed Rossby gravity wave, presence of mixed Rossby gravity waves from the observation. Say, for example, we have Rama mooring observation, right? In the equatorial Indian Ocean, it observes such mixed Rossby gravity waves. Now, let us see how this mixed Rossby gravity wave evolves and how it propagate along the equator and where it can radiate towards the north. Say, for example, some wave after reaching the east, it can radiate as Kelvin wave along the coast. So what will happen if you have a Kelvin wave in the Bay of Bengal along the coast? So all on a sudden, without any forcing locally in a particular coast, you will have some wave propagating downward direction, isn't it? So where is it coming from? The equatorial region. Not necessarily mixed Rossby gravity. Any wave can emanate through the equator, from the force source region and then propagate as a Kelvin wave. So this is important because if you make the measurements of the coastal currents in the Bay of Bengal, so you will see such a forcing which is remotely coming from the equator and locally coming from force at the local place and interior forcing in the Bay of Bengal due to the local winds in the interior of the basin. So all these three combination you often find in the coastal current of Bay of Bengal or Arabian Sea. The wave can still propagate this in the Arabian Sea. So today, using our simple code, let us demonstrate how this is happening, and let us see how a mixed Rossby gravity wave looks like and what are the cross equatorial flow associated. This cross equatorial flow is important because it can transport salinity and temperature component across the equator. So it will help the equatorial balance of the salt budget and other tracer budgets are also. So what I have done is we have a code available with us, right? So you can simulate it. So what you have to do to simulate is that in your code, you just force the equator with a forcing similar to a V wind forcing, not tow Y. You can call it tow Y wind forcing if you force it, and don't keep it a constant forcing. Rather, you change the forcing frequency in time. Like give a periodicity of forcing. Say, for example, roughly you can give a periodicity of 20 day, positive wind and negative wind, and positive wind and negative wind. So this periodicity can be 20 day this periodicity. So one wavelength this is the wind forcing tau x tau y. Okay, this is positive and this is negative. So if you give such forcing, you will see the waves of this shape is emanating from the region and it is propagating all the way to the coast. So in your model, however, you do not have proper coastal geometry. But I will demonstrate today with a model setup with the proper coastal geometry how these waves are propagating in time. So I have produced a small movie of mixed Rossby gravity waves for you, and I am going to show this, show it here. MRG. Yeah. So let us spend some time to understand this. It's going very fast. So see what happens here. This is a typical structure of mixed Rossby gravity wave. See, what I did is I forced this area with the wind stress flowing to the north, wind stress blowing to the north, and then periodically changes to the south. So that type of oscillatory forcing, I just kept at a position around the 65, 70-degree east. See now, because of the wave emanated, so wave has a asymmetric structure. You see that there is a negative on the top and positive on the bottom. And see the cross equatorial current. The currents are purely cross equatorial. So you can see the currents from south flowing to the north and north flowing to the south. So this kind of situation is very common in Indian Ocean. So you can see that Indian Ocean experiences mixed Rossby gravity waves. They propagate westward phase and eastward group. So you'll see that the group is propagating east. And at the eastern boundary, we study a paper yesterday, right? How the wave reflects and radiates at the eastern boundary. You can study the portion. I think the portion number, section number C or D, the inertia, the mixed Rossby gravity waves or Yanai waves, how they reflect at the eastern boundary. And these waves now starts to propagate along the coast, and that a person sitting in the Andhra coast or in the Chennai coast will tend to see the radiated component coming from the equator. So that they will call as a remote forcing. Okay, so let us see how this wave evolves. So this is, I think each frame is around 3-day time or a daily time. I think I don't remember. So anyway, let us focus. So you see how the wave is propagating. Very interesting. Individual waves are propagating to the west. So that's called the phase of the wave. But the presence of wave is already reached in the east. Why? Because that is a group. Now the group is slowly shifting to the east, and individual waves, the group has gone more and more to the east. So let us play that. This kind of a fast movie. So let us play this again. So individual waves are moving to the west, but the group itself is reaching to the east at some time. And you can see that Kelvin and Rossby waves are emanating through the boundary. You see that again? You can see that it's reaching the east. Yes. Then when a Kelvin wave goes, another negative Kelvin wave, positive Kelvin wave, they are keep propagating. Now you look at the equatorial Indian Ocean. There's a lot of interesting MRG type of asymmetric structure, right? Positive in the negative in the north, negative positive in the south, and positive in the no negative. And the current patterns are very interesting. The sea surface current, see, it's a pure cross equatorial cell with like a oval shape, multi oval shape. Those are all associated with the face of the wave, right? And what happens at the boundary, these individual waves radiate as Kelvin wave. They are going all the way to the Bay of Bengal. You see that there is a positive, there is a negative, it is also circulating to the Arabian Sea. So they are radiating all the way, they are propagating along the coast all the way to the Bay of Bengal, and then coming back to the Arabian Sea and propagating all along the coast. So that's what they call it, remote forcing from the equator, right? So these equatorial waves can reach your Bay of Bengal or Arabian Sea. Let's play this again one more time. Closely observe. This time you observe the Bay of Bengal coast. See, there are keep on Kelvin waves keep on coming there according to the periodicity of the impinging incoming mixed Rossby gravity wave. So the periodicity of the Kelvin wave will also, if you plot a time series of the data in the Andhra coast here, what you will see? Systematic oscillation of sea surface height. That is what exactly you see. So they are not locally driven. There is no local forcing given, but all the way coming from the equatorial region. So that's what we say, that the Indian coastal region like western coast and eastern coast are under the influence of remote forcing, the forcing coming from the equatorial region, because they are very close to the equator. So these waves can keep on move around and along the coast and reach in various part of the Bay of Bengal and Arabian Sea. So this is now what will happen if I draw the typical phase diagram of this? Can you imagine the phase diagram of this will be looking like what I'm going to draw here as this, the phase diagram or the Homuller diagram. Okay, we can call it Homuller diagram. What will be the Homuller diagram for this particular case? Let me draw the, what is Homuller diagram? The plot with the temperature in y-axis and space in x-axis, right? So this is called Homuller diagram. So if I draw the Homuller diagram, say this is, for example, 40° east, and this is 140° east, and this is a time t equal to 1 day. So let us say time t equal to 90 day. Okay, so what will happen is that individual waves were moving westward. We have clearly seen that. So let us draw a positive wave or a red color wave. They were struggling to move westward. So this is what you will see in your phase diagram, right? So and then what had happened, the blue wave also tried to move westward, but the group has taken it further to the eastward direction. So this is what you will see for a typical Homuller diagram of that. We can complete it because this is a space there. We can complete it, and another red color wave we will go. So this is kind of exaggerated. Okay, this group speed is exaggerated. May not be the real case. Group speed may not be that strong as the phase speed, but still, as an exaggerated cartoon, we can understand this better. So this is the kind of structure you are going to get for this particular wave. Now, what is the phase velocity? Phase velocity is nothing but the velocity of the slope of the contour. So this slope theta is equal to the velocity of the phase speed, or the phase speed of the wave, or velocity of the wave. What is the group speed? Group speed, to get group speed, you need to connect the center part of this wave, and that will be your group speed, and that is actually going to the eastward direction. So this is an eastward phase, and westward group. So this is the Homuller diagram of sea surface height anomaly you are going to get if you plot for this particular experiment. So this is a kind of Homuller diagram is very common. If you plot if you filter your sea surface height data provided by the satellite, your sea surface height data, if you filter for a periodicity of 30, 20 to 60 day or 30 to 60 day periodicity, if you filter it and plot the Homuller, this is exactly what you're going to get most likely, especially towards the western boundary of the Indian Ocean, western part of the equatorial region. You see that MRG waves are emanating with westward phase and eastward group. This will be very interesting to see also. And these waves, after reaching here, which is the boundary, 140 is our boundary, right? After reaching here, these waves will impinge on this coast, and then what will happen? It will emanate as coastal Kelvin wave, as we have seen in the movie earlier. You can see that coastal Kelvin waves are emanating along the Bay of Bengal, circling all the way to the Arabian Sea and keep on going. Okay, so these are the remote influences of one of the examples of remote influence. That is not the full story. Even Kelvin wave and Rossby wave itself can reach as a coastal Kelvin wave to the Indian coast, right? So not necessarily mixed Rossby gravity. All types of wave impinging on the east coast, eastern region, equatorial region, can radiate or propagate along the Indian coast and reach a Bay of Bengal or Arabian Sea. This is possible. So this is one typical example. Let's play the movie one more time to understand. Individual phases are moving, group is moving eastward, and the individual waves are now hitting each other, and the phases are nicely moving westward. You can see in this particular plot. Okay, so this is an example of a mixed Rossby gravity waves as per our diagram. Our diagram here in the dispersion curve. So all sort of these waves can be simulated using the code we have. So what was the region we simulated? We simulated some wave somewhere here, mixed Rossby gravity waves. Westward propagating phase and eastward propagating group we have simulated. So if you want to simulate an MRG wave of here, it will be of a slightly difficult part to simulate, because you may have to give a very high frequency up and down oscillation. So that's then you may get successful to generate some gravity waves in the MRG region. You need to have a very high frequency forcing. Okay, so this is one thing I need to mention. So I think this is I'm concluding my the discussion of the numerical simulation of the code here. So you can utilize the code for various purposes and you can simulate. So now, saying so, let us go back to the situation where we discussed where we can apply this equatorial wave theory in in the real case scenario. So one such scenario is ENSO. So to teach ENSO, let me depend on some predefined notes. Let me open some notes. So I think all of you know what is El. I'm not going to take a complete teaching of El Nino here, but let me give some description of El Nino. I think you might have heard what is El Nino, right? So if as a definition, if somebody asks you what is El Nino, we can say El Nino and Southern Oscillation is the aperiodic occurrence of warm SST anomalies in the central to the eastern equatorial Pacific and associated weakening of the trade winds over it and shifting of the convection center to the central to eastern Pacific. So this is the kind of a single sentence definition of El Nino. This is not very accurate, but most of the observed features of the El Nino you can find out from this definition. So let us read it again. El Nino Southern Oscillation is the aperiodic occurrences of warm SST anomalies in the central to the eastern equatorial Pacific and associated weakening of the trade winds over it and shifting of the convection center to the central to the eastern Pacific. So how an El Nino can be pictorially represented? You can do a pictorial representation of El Nino can be given as I am going to draw here. So if you have the tropical Pacific, let us draw the vertical section, okay? Or maybe both, or maybe I have a diagram already here. I don't have to draw it here. Let me check if I have a ready-made diagram there. I think I have a diagram here. Yeah, very good. This is the typical structure of El Nino. What is shown here? Tropical Pacific. You all know by now what is this boundary. This is North American continent, South American continent. This is a Western maritime continent, right? And this is a XY plane. So during El Nino, what happens? Positive El Nino, there will be a strong warm SST anomaly develops in the Eastern Tropical Pacific. And if you look at the XZ section, say for example XZ, sea surface is drawn here, then the anomalous structure of the El Nino appears like that. There's a Walker cell which is reversed in direction. Not necessarily reversed, it can be anomalously weaker also. So when you draw the Walker cell anomaly, it may appear as they are in the reversed structure. That means the trade wind is opposite direction and upper air easterly is in the aloft and convection is mostly to the central to the east and the subsidence is in the western part of the warm pool. So this is a typical Walker cell anomaly during a canonical El Nino. And if you look at the thermocline below the ocean surface, usually the thermocline in the Pacific Ocean is deep in the west and shallow in the east. And during the El Nino time, this thermocline kind of get relatively flatter or more and more flatter. The eastern thermocline get deeper and deeper. So this is called a typical El Nino characteristics of the tropical Pacific. Okay, now let us see the feedback also. Let us not forget about feedback. So what is a feedback? It is the coupling between various cause and action, right? And through certain couple or coupler, so that a particular sign is associated with the outcome. So here let us talk about the western warm eastern Pacific. Okay, if the what happens if the eastern Pacific is warm, what will happen is the SST gradient decreases. So whenever I connect two boxes with a tail end of the arrow, assume that is a negative coupling. That means that the increase in the left hand side box will cause a decrease in the right hand side box. That is what the connection, the coupler or negative. Okay, the tail end of the arrow. So when the warm eastern Pacific SST increases, that SST gradient decreases. Because of SST gradient decreases, what happens? The atmospheric pressure gradient decreases. So both the boxes are decreasing. So I am connecting with a positive end of the arrow. That means the SST gradient decreases, pressure gradient also decreases. Pressure gradient between east and west. When the pressure gradient decreases, trade wind increase or decrease? Trade wind will further decrease. So this is again a positive coupling. And when the trade wind decreases, what happens? Warm eastern Pacific SST again rises. There are two reasons for that. One is that the weakening of the trade wind actually impels some Kelvin wave to the east, as well as the upwelling of the in the eastern part is reduced because of trade wind is weakened. When there is a trade wind, there is a consistent upwelling in the eastern tropical Pacific. That is a kind of a mean pattern of the tropical Pacific, right? When the trade wind weakens, this upwelling weakens, which also contribute to the warm of the SST. So again, trade wind weakens. If this weakens, warm SST increases. So that's why this is a opposite coupling, right? This is negative coupling. If warm SST increases, again this keeps on in a loop. So what is the total sign of the feedback loop? There are two negative coupler and two positive coupler. So you can multiply all of them, you get a net positive sign. So this is called the jerkiness feedback. The jerkiness feedback of El Nino evolution is plotted here, is shown here. So you will see there is a consistent positive development of El Nino type of signal in the tropical Pacific. What is the problem with a positive feedback loop? A positive feedback loop is an unstable loop. Okay, so it is going to grow indefinitely, right? So it may reach a runaway condition or runway condition. So therefore this jerkiness feedback cannot explain El Nino in their entire history of El Nino. Maybe at some part of the El Nino, say in the development and maturing stage, the positive jerkiness feedback explain. Then how this positive jerkiness feedback collapses and the Pacific comes back to its normal state. And there is where you need this theory of wave dynamics we teach you. There you need the tropical wave dynamics to understand where is the breaking of this positive coupling happen and who helps to break the positive coupling. Okay, so to understand this better, there is a very easy way you can do that. What you can do that is what happens. Yeah, this is a particular figure. So here let us start with one aspect at first. For example, let us talk about the weakening of the trade wind or anomalously westerly trade wind. Okay, anomalously westerly wind burst. You can see when my mouse pointer is moving along that wind. So if you have this type of wind anomaly, what is the response in the ocean? We already studied. Kelvin wave is going to propagate to the east and Rossby wave is going to propagate to the west. We already know that. And this Kelvin wave will keep on pushing down the thermocline to the down. So that will help also the warming the SST in the east. Okay. In addition to that, the weakening of the trade wind also reduces the upwelling of the water in the eastern equatorial Pacific, due to which also the SST can increase there. So as a consolidated effect, during positive El Nino, SST in the eastern part of the tropical Pacific increases. So now you can at least imagine what happens a wind burst as shown in this particular arrow given to the ocean. This is depth. Okay, this is a cross section XZ section shown here. So when the wind is impinging on the coast or anomalous wind forcing is given, immediately a positive Kelvin wave going to emanate to the right direction and a negative Rossby wave going to emanate to the left direction. So this is the first step to explain how a positive feedback can be explained during El Nino. So this situation will reinforce this phenomenon because of that SST increases, pressure gradient decreases. SST gradient decreases, pressure gradient decreases, trade wind further weaken, which again increases the warm eastern Pacific SST. So that is the first positive feedback part of the system. Now, where is the negative feedback coming from? It's a very important question. You know that the ocean boundary is bounded by the continents, right? And when the wave reaches the eastern boundary, you know that some part of the Kelvin wave is radiating towards the north or south, but the remaining part will reflect as a Rossby wave. Then what happened to the Rossby wave came to the left, it reflects at the western boundary and hit back as a Kelvin wave. So there is a tendency, it's a possibility that this incoming negative Kelvin wave can interact with the previous Kelvin wave or SST anomaly there, and they can kill the SST anomaly. And this killing process can give you a negative feedback to the system. El Nino collapse, and El Nino comes back to, and the Pacific Ocean can come back to the normal stage. So whatever I have described through so far is called the delayed oscillator theory of El Nino. The name itself is very meaningful, right? Delayed oscillator theory. So let us write down that name, delayed oscillator theory of El Nino. Delayed oscillator theory of El Nino. So this word has individual meaning. What is delayed? Something happening by a delay of something. Oscillator is very easy to understand. What is oscillating? The Kelvin wave becomes Rossby wave becomes Kelvin wave. That can be the oscillation, the theory of El Nino. So what is this delay? Delay is actually due to, so you know that when the tropical Pacific excites such a Kelvin and Rossby wave in both in opposite directions, it hits the boundary and it takes some time to reflect and get back to its original position. So that delay is what we are talking about. Suppose if you have a Kelvin wave in the El Nino type of situation, This Kelvin wave goes in the coast, and some part comes as Rossby, right? So returns as Rossby, and this comes this direction. And the earlier Rossby, for example, I can draw it in the blue curve. This is the earlier Rossby waves where we have drawn earlier, and this comes back, hits the western boundary and comes back as a negative Kelvin. Okay, this comes back as a negative Kelvin. So what are the the time scale associated with this travels at 1/3 of the speed, and this travels at a speed of c. So this difference in the propagation speed of Rossby and Kelvin sets up certain delay when they can meet each other in the next session, and that delay is necessary for the El Nino to grow. If you take the time scale of El Nino start with April, May, June, July, August, September, October, December. The next year, January, February, March. This is the life evolution of an El Nino. This anomaly, for example. Okay, this axis is the SST SST anomaly. Okay, and this is time. So this is the life cycle of El Nino starts to mature, and this part maybe you can assume as the Kelvin-Rossby development and propagation. Then it matures in by December. By the time the reflected waves going to come and contribute to diminish the signal and return the Pacific back to its normal state. So this propagation of Kelvin wave and Rossby wave is very useful for establishing a theory called delayed oscillator theory of El Nino. So let us see a three-dimensional picture of that. I was trying to draw in one of the previous pages in earlier discussion. Yeah, this is exactly what happens during El Nino. So this is a three-dimensional picture of tropical Pacific thermocline. So I'll help you to understand. In the mean state, you can see the mean thermocline, which is a flat line, which is deeper in the west and shallow in the east. Agreed. This is 20 degrees south to 20 degree north, 0 degree equator in the middle. This may be here, this side may be 140 degree east in the Pacific, and this right side can be 290 degree east. Okay. So what happens? The mean state, the thermocline is something like a flat thermocline. On that time, the El Nino happens. So El Nino wind, can I draw it by yellow color? So this is a kind of westerly wind burst comes due to weakening of the trade wind. So let us assume this is the wind burst, due to which you have a strong positive Kelvin wave to the east. Now I have drawn the three-dimensional structure of the Kelvin wave. Now you can see how the thermocline is pushed down. It's called a deepened. I have written here deepened thermocline due to the pushing of the Kelvin wave. So this is Kelvin wave. So this is called downwelling Kelvin wave. Look at the boundary it happens. See, it is propagating to the north, also south, and the thermocline being pushed. So that is why you see more and more warm SST anomalies in the eastern part of the Pacific during a positive El Nino year. Then what happens to the west, where Rossby propagating westward? It is shoaled. Okay, the original thermocline was somewhere here. Now that is shoaled, as you see in the left side. And this is the complete establishment of a Kelvin-Rossby situation during the growth stage of El Nino, you can say. Now the story start the oscillator theory. What happens? The wave propagates both direction. They hit the coast in the eastern boundary. They hit the coast in the western boundary. They reflect back and they meet each other in the center. So this can again, so what will happen when they reflect this negative Rossby wave, which is called cooling or a cooling effect, because it's a thermocline shoaling effect, which comes back as the Kelvin, which quickly comes back to the center, and this can interact with the already existing positive SST anomaly here, so they can kill each other. Okay, so this understanding of the tropical dynamics is so essential to describe the El Nino, especially the delayed oscillator theory of El Nino. Now we can describe this descriptive points in form of equation. For example, there is a delayed oscillator theory equation also exists. This is the equation. So various theories of El Nino, the delayed oscillator theory says that the conceptual delayed oscillator theory is represented by a single ordinary differential delay equation with both negative and positive feedback. So this is the equation. So let us examine what are the terms. What is this? dt by dt, where t is the SST anomalies in the eastern equatorial Pacific. this is only a single variable equation. Okay, T is the SST anomalies in the equatorial Pacific, which represents El Nino or Nino index. So the time evolution of the El Nino equal to A times T. That means it's a positive coupling. See, as long as A is positive, the temperature anomaly will grow as per the existing anomaly. That is what this represents. Minus, there is a BT term. This is a decay term because B is negative. What happens when B is positive? This term itself minus BT become negative. That means it's a killing term. But killing term is not given at the same timing, but it is given with a delay of T minus eta. What is eta? The appropriate delay. You may call it as a 3 months of the time scale. So this decay term is given as a delayed term minus some damping term. Damping term is given for some stability. It's a higher order damping term, epsilon t cube, so that the damping term will take care further from the further growth, because some amount of heat has to definitely dissipate, irreversibly dissipate, right? So that is called the damping term still. So this is a very beautiful explanation of a delayed oscillator theory. Now where is the conceptual delay comes from? The T minus eta term. When eta equal to 0, there is no more delay. So there is, the equation is will either grow or decay according to the choices of B. That's all it will happen. But the system get an oscillatory nature if you provide a term T minus eta, where T is the in situ time and eta is a delay in time. In this case, you see that solution will be oscillatory in nature. So that means this can provide a solution which can reflect between positive and negative. Then there is an El Nino and there is a La Nina. There is an El Nino, there is a La Nina with approximate time periodicity. So the delayed oscillation equation can provide you some approximate time periodicity to the system. And where is this delay coming from? That delay coming from due to the advective reflective theory, or basically the reflection theories of the waves provide you appropriate delay in the system. The wave has to go to the east, hit back and hit and come back, and this wave has to go to the west and hit and come back, and they come back each other, they can interact each other, so that the anomalies of SST can kill each other. So that has some delay, and delay depends on what? The speed of the propagation, right? Here the speed of the propagation depends upon the gravity's gravest mode speed. Here in our discussion, it is G dash thermocline, He, which is will be approximately 3 meter per second. So Kelvin wave travels at this speed to the east, Rossby wave travels 1/3 of the speed to the west, and because of the difference in the speed, to reflect and get back to its original position, you will have some delay, and that exactly the delay you have to supplement in this equation, so that the T term, what is T? The SST anomaly in the Eastern Tropical Pacific will develop a oscillatory nature. Whenever a signal is in oscillatory nature, what is the net feedback involved in it? A negative feedback or negative feedback diagram. Okay, whenever there is a system is oscillatory in nature, so you have to you can represent system in two basic states, right? It only is in a equilibrium situation, which is oscillatory, positive, negative, positive. So this is typical example of a negative feedback process, negative feedback, because that only give you a consistent oscillatory nature. If positive feedback, either it grow or it decay. That's what it does. Okay, but therefore Illinois is a negative feedback eventually, because it has an oscillation. There is a positive Illinois, after few years again a negative Illinois or La Nina, again it comes to positive Illinois, and this is one a way of describing it. That means that it's a negative feedback mechanism. So where is this negative feedback coming from? So one explanation is the delayed oscillator theory. So this is one real application of the theory we have studied, how to explain El Nino using a delayed oscillation of reflection of waves between west and east of the tropical or equatorial tropical Pacific. Okay, so it's a direct application. So you can with this you will be able to explain what happens in this. And now there can be a misunderstanding possible here. So people will think that the SST, with this explanation, it is easy to assume that the El Nino starts to have a positive anomaly from the central Pacific and then going to the east, because Kelvin wave is like that. But that's not actually the case. The time evolution of the El Nino is the other way around. So what is the time evolution of El Nino anomaly? So this is a Hohmuller diagram of El Nino Homular diagram of as El Nino related SST anomaly in the tropical Pacific. This is 150-degree east, 200-degree east in the right hand side, and is starting with January, February, March, April, May, June, July, etc. to December, and then again going to the next year. So year 0 is the El Nino year, year +1 is the year after the El Nino year. So here, this is the typical canonical El Nino homular diagram of SST anomaly. So this gives you an impression of a kind of a westward propagating wave, but it's actually not that. So I think you are understanding my point, right? So so far I was telling Eastern Pacific will have a Kelvin wave effect and there will be a warming SST, but then you expect a homular diagram angling to the right side, isn't it? But that's not actually happens. The reason is that you have to examine the three-dimensional structure of the system, okay? Or maybe here for example, the mean thermocline is deep in the west and shallow in the east. So due to the weakening of the trade wind, the upwelling weakens first in the east. Okay. And because of the weakened upwelling, the warm SST anomalies start to build up in the east of the Pacific, not in the central Pacific. Then slowly the upwelling weaken and weaken, more and more anomalies start to propagate to the west. That's why the homular diagram of El Nino, canonical El Nino, looks like this. This don't interpret this is directly related to a Rossby wave because it is propagating westward. That is not the truth. Okay, this is the net combination of the wave effect, weakening of the upwelling effect, etc. in SST. That's why the homular diagram of El Nino SST anomaly looks like this. But if you draw the sea surface height anomaly, you will get a clear picture of eastward propagating Kelvin wave during El Nino time. Okay, sea surface height if you are floating, and if you plot the sea surface height in the 4 degree south or 4 degree north, you get a clear westward propagating Rossby wave signal. Okay, so anyway, I'm not going to teach further into the El Nino theory because that is not our focus here. Our focus here is to utilize or encash what we have studied about the tropical dynamics of Kelvin Rossby, simple linear theory, how you utilize to understand something, a very interesting phenomenon like El Nino, a real size phenomenon like El Nino, using a delayed oscillator theory. So according to the delayed oscillator theory, it says that uh, the delay due the delay due to the delay raised by the time required for the waves to reflect from the boundaries will set up a negative feedback to the system, which brings the El Nino state back to a normal stage. Okay, so that is one interesting theory of the El Nino. But El Nino is not a delayed oscillator theory. Will give you a simple, harmonic solution, simply periodic solution. But El Nino doesn't happen as a periodic solution. Is El Nino a periodic solution? No, El Nino happens more chaotically. I mean, it may happen anywhere within 2 to 5 year or 4 to 7 year time scale. You can say that. But there is no guarantee or surety that if El Nino happened in this year, immediately after 4 years there will be El Nino. No, it can be anywhere from 2 to 7 year window. So that's why it's called a chaotic phenomenon. So it is much complex than what we have discussed, but the very essence and fundamental of it is able to say about by the reflection theory of the wave that we are still able to describe some nature of El Nino, such as how the positive coupling breaks. At least that part we are able to explain by this wave reflection theory. Okay, so that's why the delayed oscillator theory is one of the useful theory in explaining a simplistic narration of El Nino, why El Nino changes between El Nino to La Nina to El Nino. Okay, so this is one important aspect. So I will go back to, I'm not going to teach more on the El Nino part. So I think I have basically come to now maybe before concluding I have one more real size, because our purpose is to introduce you the real size problems. I mean that means what we have studied in the lab, it's okay as a good as a theory we can study and understand, but we have to interpret or we have to carry this forward further to the real size application. So El Nino is one such application I have mentioned. Then let us come back to one more aspect of the system. But suppose if you are given a set of data in your hand, say it be sea surface height anomalies, or say it be Euler data, or say it be wind data of equatorial region or a tropical region, how do you bring out the presence of these waves in those data? So that's a critical question. The theory should not stand as an individual independent theory from the real world. You should be able to associate the theory to the real time application. Otherwise, there is no value of studying all this. One such example I teach you is definitely the MRG waves, what we have seen. I think I am unable to navigate, or maybe let me see. No, I'm unable to navigate. Anyway, we were able to explain the mixed Rossby gravity waves that we have studied, which occurs in the tropical Indian Ocean, etc. We studied. Similarly, suppose if we have a raw data, an OLR data, outgoing long wave radiation, which represents the cloudiness, or wind data, low level wind or high level wind, how do you extract the presence of these waves? So to understand that, I'm going to introduce you a very interesting paper, maybe the next half of our discussion. That will be our last discussion also. That there are certain methodologies we can adapt over a data. Say, for example, some filtering techniques, etc. And using that techniques, you will be able to discern certain wave features. That's the wave that we have studied. And I mean, the other way of putting the question is that the question is very simple. I think I don't know where is my here. So where are these? I mean, can you construct a wave number frequency diagram from a raw data? That is the most simplistic form of my question. From a raw data, can we construct this diagram? From this diagram, we understand the structure of the wave, fine, through analytical solutions. But from a data, raw data that we measure through satellite or any other meaning, can we construct this wave number frequency spectra or wave number frequency diagram? Or can you represent the power of the wave in this diagram, in this phase? I mean, wave number frequency space. Then we can believe, yes, this theory, whatever we have studied, is actually available in the real time observation. Then only we will develop a confidence. Okay, so that is one part we can do that. So to do that, there was a classical paper published in 1999 or somewhere. We're going to discuss that today. Is by Wheeler and Kiladis. So they have did similar filtering techniques to extract the power available in each of these wave in a raw data. Raw data they depend upon is outgoing long wave radiation data. They taken it up, and then they have applied rigorous filtering exercises and some methodology called wave number frequency spectra analysis. So that analysis is some interesting analysis. I'm going to discuss the after the break now today. And using that, they were able to see, yes, in the tropical region, if you examine the outgoing long wave radiation or cloudiness data, there are presence of Kelvin wave, there are presence of Rossby wave, there are presence of mixed Rossby gravity wave. Everything is embedded in the data. Even MJO, there is presence of MJO. MJO is not coming in anywhere. As I said earlier in our discussion, we have he started propagating only one component in the low wave number, which is Kelvin wave. Okay, but we don't have a MJO. MJO is a Kelvin lookalike wave, but that's not a Kelvin wave. It travels with much low frequency, and whose dispersion curve supposed to come here, but we did not get anything here. In our theoretical discussion, we failed, right? This MJO was not able to produce in our shallow water equation. That itself shows that it is not just the scale of certain shallow water equation. It may have much more complicated phenomenon involved in there. So that's why we are not getting. I mean, if in the raw data, all these things we can extract. So the how to extract these things in the raw data is maybe my final discussion by connecting the theory what we have studied in the classroom and how we can see in the real scenario in an observation. So that's what I will discuss in the next step. So maybe we can take a 5-minute break here and then come back by 3:05. Yeah, we can take a 5-minute break. We'll come back at 3:05. Okay.
Okay, we can take.
Yeah. Okay. Yeah.